Welcome to the solution of the exercise on definite integrals. We should consider the area A1 of the circular sector of radius 6 and a known external angle alpha. Moreover, we should consider the area A2 of the region of the plane comprised between the curves f1 of x, which is equal to square root of 3 over 2 pi squared minus x squared, and the function f2 of x, which is equal to sine to the fourth of x plus sine squared of x minus 7. The variable x is varying between minus 3 over 2 pi and 3 over 2 pi. We should find the value of alpha for which the two areas, A1 and A2, are the same. Let's start by evaluating A2. This is the area comprised between f1 of x and f2 of x. Then, it is equal to the difference of the definite integral of f1 and the definite integral of f2. These definite integrals are between minus 3 over 2 pi and 3 over 2 pi, because this is the interval where the variable x is varying. There is a simple geometrical interpretation of this formula. In fact, the area A2 can be seen as the sum of the area subtended by f1 of x and the area subtended by f2 of x. The reason for this minus sign is that since f2 of x is a negative valued function, the value of this integral will provide the area subtended by f2 of x multiplied by minus 1. Let's start calculating the area subtended by f1. In theory, we should compute this integral. However, it's much easier to observe that the value of the integral is nothing else than the area of the semicircle of radius 3 over 2 pi. We can immediately write that the value of this integral equals 9 over 8 times pi cube. In other words, the radius squared, 9 over 4 pi squared, that multiplies pi over 2. Let's turn now to the area subtended by f2 of x. As we have seen, we should calculate this integral. In order to do that, we should first calculate the indefinite integrals of sine to the fourth of x and of sine squared of x. Let's start by calculating the antiderivative of sine squared. We want to compute the antiderivative of sine squared of x. I propose to use the rule of integration by parts. We can write the sine square of x as the product of two sine functions. And then, by applying integration by parts, we obtain that this is equal to the antiderivative of sine of x, which is minus cosine of x, that multiplies sine of x, minus the antiderivative of sine x, that multiplies the derivative of sine x, which is cosine x. Reworking this out, we obtain minus cosine of x sine of x, minus and minus plus antiderivative of cosine squared of x. Now you should recall the trigonometric identity cosine squared of x equal 1 minus sine squared of x. Now we can substitute this expression for the cosine squared of x, obtaining minus cosine x sine x plus the antiderivative of 1 minus sine squared of x. Then we obtain that this is equal to minus cosine of x sine x plus, by linearity, we obtain x minus the antiderivative of sine squared of x. Let's rewrite this more clearly. You should notice that the antiderivative of sine squared of x is at both sides of this equality. Then we can bring this term to the left-hand side, obtaining 2 antiderivative of sine of x squared that equals minus cosine of x sine of x plus x. Thus, the antiderivative of sine squared of x is equal to x minus cosine x sine x divided by 2. You should notice that this equality is valid up to an arbitrary constant. Here we summarize what we have found. Let's turn now to the computation of the antiderivative of sine to the fourth of x. We want to calculate the antiderivative of sine to the fourth of x. I propose to use again integration by parts. We write sine to the fourth of x as the product of sine of x and sine cubed of x. Then, by using integration by parts, this is equal to the antiderivative of sine of x, this is minus cosine of x, that multiplies sine cubed of x, minus the antiderivative of the antiderivative of sine of x, again minus cosine of x, that multiplies the derivative of sine cubed of x. This is 3 times sine squared of x, that multiplies cosine of x. Reworking this out, we get minus cosine x sine cubed of x, minus and minus plus antiderivative of 3 times cosine squared of x that multiplies sine squared of x. Again, we should use the trigonometric identity cosine squared of x equals 1 minus sine squared of x. We can substitute this expression for cosine squared of x, obtaining minus cosine x sine cubed of x plus 3 times the antiderivative of 1 minus sine squared of x that multiplies sine squared of x. This gives minus cosine x sine cubed x plus 3 times the antiderivative of sine squared of x minus 3 times the antiderivative of sine to the fourth of x. Similarly to the previous case, we should notice that the antiderivative of sine to the fourth of x is appearing in both sides of this equality. Then, by bringing this term to the left-hand side and divided by 4, we obtain that the antiderivative of sine to the fourth of x is equal to 3 times the antiderivative of sine squared of x minus cosine x sine cubed of x divided by 4. By substituting the expression for the antiderivative of sine squared of x that we have just found, we obtain that the antiderivative of sine to the fourth of x is then equal to 3 over 8 that multiplies x minus sine x cosine of x minus 1 over 4 that multiplies cosine of x times sine cubed of x. We can now calculate the area subtended by f2 of x. It is sufficient to substitute in this integral the expressions that we have found for the antiderivative of sine squared of x and for the antiderivative of sine to the fourth of x. Of course, the antiderivative of 7 is trivially 7x. This definite integral will be equal to the antiderivative of this expression evaluated in 3 over 2 pi minus the antiderivative of this expression evaluated in minus 3 over 2 pi. By linearity, we obtain that the antiderivative of this expression is given by this expression. Then, evaluating the expression in 3 over 2 pi gives minus 147 divided by 16 times pi. Evaluating this expression in minus 3 over 2 pi gives plus 147 divided by 16 pi. Subtracting the two values gives minus 147 divided by 8 pi. Now we can evaluate A2. Recall the value for the area subtended by f1 of x that we have found previously. The area subtended by f2 of x with sine is this value. Then the difference between these two values gives 9 over 8 times pi cubed plus 147 divided by 8 pi. Let's turn to the evaluation of A1. It is relatively straightforward to find the area of the circular sector even if you don't remember the formula. In fact, the area is to the internal angle of the sector, as the area of the entire circle is to 2 pi. In our case, the area of the circular sector, A1, is to the circular sector internal angle, which is 2 pi minus alpha, as the area of the circle, which is pi times the radius squared, in our case 36, is to 2 pi. Multiplying the corresponding terms, we obtain that 2 pi times a1 is equal to pi times 36 times 2 pi minus alpha. Then a1 is equal to 2 pi minus alpha over 2 pi that multiplies 36 pi. Given the value of a1 that we have just found, and given the value of a2 that we have found previously, we can find alpha by equating the two areas so that a1 equals a2, and we can solve this simple first-order equation with respect to the unknown alpha. This gives alpha equal to 47 divided by 48 times pi minus pi cubed over 16. This value is approximately equal to 1.14. This completes the exercise.